Hey guys, hope you're all doing good and welcome to a new video. In this class, you will be learning how to perform simulation of a simplified battery thermal management system. So the geometry has been shared with you and the boundary conditions will be discussed in this particular lecture. We will be going over how to set up this problem from scratch. As I'm setting it up, I'll be explaining the thought process behind several model choices that I'm making. Now, please do remember that this is an introductory level course and hence I will not be able to go in depth with respect to physical models that's being used and the math behind them, right? So I want you to kind of trust me with the model choices that I make. All right, so that being said, let's get started. All right guys, so let's go over the learning objectives of this video. By the end of this video, you will definitely be a bit comfortable about using Ansys Fluent to simulate battery thermal management systems. Right, so in this video I'll explain the problem statement, make sure that you understand the boundary conditions and initial conditions that are required for the problem. You will be able to understand what type of material properties has to be provided, and then you will be able to understand what additional physical models that we use for this simulation. And finally, by the end of this video, I would have given you a full demo of how to set up a basic BTMS simulation from scratch, and we'll take a look at some results and discuss those results. So most of you might already know what Ansys Fluent is. It's a very powerful computational fluid dynamics software and can be used for a wide range of CFD applications. In this particular video, I will be demonstrating how you can simulate the flow through a simple BTMS that is shown here. In this case, it has 5 cells. This is going to be the inlet. So air is going to come through the inlet, and as it actually interacts with all these cells, it's going to remove the heat that is generated from these cells by forced convection. Our idea is to understand what the steady state temperature is going to be of these cells when the incoming air is flowing at a particular velocity. Now the heat generation in the batteries is modeled by a constant volumetric heat source. So you would essentially say what is the volumetric heat source per cell, and volumetric heat source as a unit of watts per meter cube. So you will be calculating the volumetric heat source for this final project. As far as the boundary conditions goes, the inlet velocity is assumed to be 3 meters per second, and the other thing that you need to calculate, as I mentioned in the previous slide, is the volumetric heat source. With respect to material property, I'm going to assume that my solid cell is made up of aluminum, so the thermal conductivity and specific heats of aluminum will be used. Now, is this correct? Well, that is something that you are going to be figuring out as part of your project. You should also figure out what properties are needed to model the cell correctly, and you need to kind of evaluate if the original assumption that I have made is correct or not for this particular problem. As far as physical models are concerned, since we are interested in the steady state temperature distribution, we are using a steady solver, and we are basically using something called as density based solver. Now typically for CFD there are two types of solvers, density based solvers and pressure based solver. Since this is an introductory course, we are not going to be talking about how density based solver and pressure based solver works. So the only thing that I want you to remember is when the Mach number of the flow is greater than 0.3, it is always better to use density based solver. In fact, if you are dealing with air, it's fine if you use density based solver. If the velocity is a bit low, then it might take a bit more time, but your solution is guaranteed. So that being said, with respect to Ansys Fluent, you can actually use the pressure based solver for even high Mach number flows, up to 3 to 5. However, for the purpose of this tutorial, we will be sticking with the density based solver. Energy is turned on. So when we say energy is turned on, that means energy equation is also being solved. In addition to this, we are also simulating turbulence by enabling the standard K-epsilon turbulence model. So as far as results, before we jump and run the simulation, I kind of wanted to show you a sneak peek of what you can expect. So here you can see that these are the governing equations that you're solving. Continuity equation for mass balance, XYZ velocity, which is nothing but XYZ momentum conservation equations, energy, one equation for turbulent kinetic energy and one equation for turbulent dissipation. In the graph, x-axis is the iterations and y-axis is the residual. In general, you want to make sure that your residuals drop. That alone is not going to be the criteria. You should also look at some type of physical quantity. For example, here I'm looking at the volume average of temperature across all my solid cells, and I'm plotting that as a function of iterations. You can kind of see that somewhere after 350 or 375 iterations, the results don't change much. And this is what you call as convergence, right? So you can see that the results deviate less than 5%, right? So that tells you that for this particular operating condition, if you run the problem for 450 iterations, you can expect a steady result. Now keep in mind that this observation has to be made for each and every CFD problem that you might simulate in the future, because you never know for which problem how many iterations are required. Alright, so that being said, let's get started with Ansys Fluent. Alright, so here I've opened Ansys Workbench 19.1 and I'm going to select Fluid Flow Fluent and I'm just going to drop it to the canvas here. Right click on geometry and select new space claim geometry. Alright, so once space claim has opened, click on file and click on open, and you will be loading the BTMS geometry file that has been shared with you. Please note that the extension is scdoc, which means that this is a space claim file. So once we open it, you would basically see a model tree which contains something called as component 2, fluid volume and cell. So let's take a look at each of these individual components. So the cell refers to the individual cells that you have. The fluid volume basically refers to the volume that's occupied by air, and you can see that the fluid volume has cutouts for the volumes that the cell occupies. And then you have something called as component 2, which is the casing, right? So this is the casing that's basically holding the entire fluid volume and the cells, which we don't want for this simulation, and that's why you can see that this has been suppressed, and you can see that there's a cross mark here. So we will need only fluid volume and cell. Now space claim is an amazing parametric CAD modeler which can be used for geometry cleanup and geometry preparation for CAE simulations using Ansys products. Now in this basic course, we are not going to be diving deep into how geometries can be created, and hence once you have completed this step, you can close space claim. So the next thing that we are going to do is meshing, so I'm just going to double click on it. Alright, so looks like the geometry has loaded. Rename. The first thing that we want to do is we want to create named selections. So we are going to name the inlet and outlet boundaries so that we can apply boundary conditions in Ansys Fluent. So I'm going to use the face select option, left click on this particular face, and then use right click and select create named selection, and I'm just going to type in inlet. Now to rotate the geometry, use the middle mouse button and just turn the geometry. Click on this face, left click on that face, use the shortcut key N and type in outlet. Alright, so now what we want to do is, we know that the gray body is the fluid volume, so I'm going to go to the body select option, click on this guy, use the shortcut key N, and I'm just going to call this as the fluid volume. And while the body is selected, right click. Looks like I lost the selection, so let me select it again. Right click and click on hide body. So this move will expose the cells that are present. Use Ctrl plus middle mouse to pan, and use the middle mouse to zoom. And what I'm going to do is, I'm going to make sure that body option is selected. I'm going to left click, hold my mouse and just drag over all the individual cells. While doing this, make sure that you do not let go of the mouse pointer. So let's try it again. Left click to unselect everything, left click, hold, drag over all the cells, and then hit N and create a new named selection, and we are just going to call this as solid cells. Then click on the mesh option and make sure that physics preference is set to CFD and element size is set to 5. So now right click and click on generate mesh. So you can see that the mesh is generated, but we are able to see only the solid cells. So right click anywhere and click on show all bodies. So here you can see that we have a tet mesh for the airflow, and we have mostly hexahedral cells for the solid cells. I'm going to use the section plane icon, click and left click anywhere, and just don't let go of the left click, drag it over the screen to create a line. So this line is essentially indicating a plane that's going to cut the geometry. Right, you can see that the geometry has been cut. Use the middle mouse button, click and rotate the geometry, and you can see how the mesh has been cut. So right now I have not cut it deep enough. I'm just going to enable the section plane, look at the geometry like this, click on new section plane and cut it like this. So now you can see the interior mesh, and here you can see that we have separate mesh for the solid cells and we have a separate mesh for the fluid cells. This right here is what you call as an hexahedral cell, whereas this is what you call as a tetrahedral cell. Now what I can do is I can click on show whole elements, and that is essentially going to tell you, that is essentially going to render the entire mesh. So if you look at it, you can kind of see that the entire thing is divided into volumes and information is shared from volume to the other volume, right, which is kind of the basis of finite volume method. So now I'm just going to uncheck the section plane, and I think everything looks good. Let's make sure that all of my named selections are there, and I'm just going to close Ansys Mesher. So let's right click on mesh and update so that the mesh information is updated. Alright, so looks like the setup is complete. So now what we are going to do is we are going to right click on setup and click on edit. This is going to open the Fluent launcher, select double precision, select parallel, and I'm just going to use up to 4 processes to run the simulation. Alright, so looks like the mesh has been loaded into Ansys Fluent successfully. So the first thing that I want to do is make sure that the solver is set to density and time based, and make sure that steady is selected. So the way Ansys Fluent works is fairly simple. You would basically work your way from left to right, and whenever required you would basically fill in the details in the model tree. So if you rotate the model, the inlet is colored blue and outlet is colored red. This information is automatically obtained when we created named selections. So let's go to setting up physics, and let's make sure that energy solver is turned on. Click on viscous and select K epsilon. You can see that the standard K epsilon model is automatically selected. The next thing that we are going to do is we are going to go to cell zones. So here you can see that the fluid volume and solid volumes are shown. Fluid volumes type is fluid because the name fluid is found there. Ansys Fluent can do that automatically. Similarly for solid cells, you can see that the type is solid. So let's click on edit, and I'm going to add source terms. Click on source term panel, click on edit, and let us say that we're going to have one source, and I'm going to say that this is a new input parameter, and I'm just going to call this parameter as volumetric underscore heat underscore source, and I'm going to initially set it to 0, and I'm just going to click on OK and click OK again, click OK again. So then we are going to go to boundaries. Here we first select inlet, we click on edit, and for velocity magnitude I'm just going to click on this drop down and select a new parameter. I'm just going to call this as inlet underscore velocity, and I'm going to set the initial value as 3 meters per second. That's basically what you need to do. You don't have to change anything else. If you're curious about the outlet boundary condition, you can see that it's a pressure based boundary condition, and we essentially say that the gauge pressure is actually 0 at the outlet. So let's click on OK. So the next thing that we want to do is, while solving the solution, we want to basically take a look at the volume average of temperature across all the cells. So this can be done via reports. So as you're solving, you want some reports. So let's click on definitions, select new, select volume report, and let's select volume average. And the report by default is going to be called as report underscore def 0. That's fine. I'm going to make sure that the field variable is temperature, and I'm going to be selecting static temperature. I'm going to be computing it only for my solid cells, and I'm going to say that this is an output parameter. So the input parameters are velocity and volumetric heat source, and the output parameter is going to be this volume average temperature. So let's click on OK. Then comes initialization. So let's select standard initialization, and I'm going to basically set the number of iterations as 500, and I'm going to hit calculate and click on yes. You can see that the simulation has started to run, and the residuals are almost flat and they're slowly dropping, but we are not seeing the volume average plot, right? So what I'm going to do is I'm just going to click on stop to stop the solution, click on OK, and we have to make sure that we hit the plot button here, and we need to make sure that we select the report that we want to plot. So click on new. It's automatically going to show you the report that you want to plot. Select it, and you can see that it's going to create a new plot window, and it's going to plot every iteration, which is what we want. And I'm just going to say OK, and I'm going to close this guy. So now you can see that we have already run like 55 iterations. Now if I basically hit calculate again, it's going to run for 500 more iterations, which is fine. So let me hit calculate, and you can see that it prompts a warning message, and I'm going to just say that we want to use the settings for current and future calculations. So let's click OK. Okay, so the plot window is not appearing. So what I'm going to do is I'm just going to click on stop one more time, and I'm going to reinitialize the solution. So that way I delete all the existing data, and I'm going to run the simulation from first. Okay, for some reason the plot is not appearing. So let me just try this one more time. I'm just going to click on stop, and I'm just going to click on OK, and I'm just going to click on plot again. And I'm just going to delete this guy, add a new plot, select this, let me just add it to the right hand side, and I'm also going to select print to console. So I think maybe last time I forgot this step, but I can't recall. So let me just click on OK again and close this guy and hit calculate to see if the window appears. So I'm just going to use the second option, click OK. There you go. So the plot appears, and you can see that the volume average of temperature is 300, right? And that is kind of expected because we are not seeing any changes with respect to the source, right? The volumetric heat source is 0, so there is no reason to believe that any heat is going to be generated. So I'm just going to wait for the simulation to run for 500 iterations, and till that time let's take a look at the scaled residuals. Alright, so looks like the calculation is complete. So let me just click on OK. And I'm just going to close Ansys Fluent. Alright, so now would be a good point for me to just save the file. I'm just going to call this as BTMS demo. Alright, so now what I want to do is I want to take a look at the results. So what I'm going to do is I'm just going to click on results, and this is going to open a new program called as CFD-Post. Alright, so this is CFD-Post, and you can see that the geometry has been loaded and certain components are not visible, which is perfectly fine. You can always enable them by just clicking on it. So here I can basically look at the solid cells, right? And let's color the solid cells. So I'm just going to double click on them and go to color, and I'm going to select variable, and I'm going to select temperature, and just click on apply, and you can immediately see that the battery pack is colored. And it kind of makes a lot of sense that the first battery is the coldest and the last battery is it kind of makes sense because the first battery gets cooled easily because the second battery is behind the first battery, right? So it doesn't experience the same amount of airflow. And if you just extend that logic, the fifth battery is going to be cooled the least. But that being said, you should look at the color scale range. We are just talking 1 degree Celsius in temperature change. That's because we are not generating any heat. So let's also create a cut plane to kind of understand how the mesh looks like. So click on, and by the way, to rotate, it's left click. To zoom in and out, it's basically the middle mouse button, and if you hold on to control, you can pan it, right? Essentially it's the same control. So I'm going to click on location, and I'm going to add a plane, and let's click on OK, and I'm just going to create an XY plane, right? So this is the XY plane, and let's just click on apply, and you can see that that's where it cuts the geometry. What we can do is we can click on the Z coordinate and just slide it to see how it actually moves, and you can set a specific number if you have that in mind, right? I'm just going to cut it so that it kind of cuts the cells exactly in the middle, at least as close as possible, right? I think that's good, and I'm going to just hide the solid walls for a second, and I'm just going to be looking at the plane, and I'm going to just color it by, say, the velocity. Right, so here you can basically see how the velocity flows. You can basically see the velocity field, and as expected, you can see that between two cells you have a pocket where the velocity is very low, right? Which is kind of expected, and that is why the second cell is cooled less, the third cell is cooled even more less, and so on. In the view, in the render option, I'm just going to click on show mesh lines, and I'm just going to apply, and you can kind of see both your solid mesh and your fluid mesh. So you can see that inside your solid there is no velocity, right? Because it's made up of solid, and that's why there is no colors there, and outside you can actually see the colors, right? So you can do a lot more post-processing. Feel free to just play with it. One thing that looks very cool that a lot of students ask me how to do is creating volume renders. So the first thing I want to do is hide the plane, and I'm just going to click on this option, which is the volume rendering option, and I'm going to select velocity, and let's just click on apply. This is essentially going to show you how the 3D velocity field looks like. To increase the resolution, I'm just going to bump this parameter to 64. Now this is going to take a bit more time to load, but you can see that the results look much more smoother, and I'm going to just increase the transparency a bit so that you can kind of see what's happening inside, right? So you can see that there are local areas where the fluid seems to be getting accelerated, right? Which kind of makes sense wherever the area of cross section is minimal, right? So when the fluid is going through this path, this is where the area of cross section is minimal, and that's where fluid tends to accelerate, right? So visually or qualitatively this seems to check out. So it seems like we have a reasonable model to start with. So I'm just going to close this guy, and I'm just going to click on the parameters that we created. So you can see that I've created a couple of parameters, volumetric heat source, inlet velocity, and this is the output, right? 300.04 Kelvin. So what I can do is I can now say change the heat source values to 30,000 watt per meter cube, and I'm just going to maintain the same velocity, and let's just click on this guy. I'm just going to retain the result. I'm going to select here, and I'm just going to right click, and I'm going to basically say update selected design points. So Fluent is automatically going to use these values, and it's going to update the setup, and it's going to run the simulation, right? The status can be seen in the bottom left corner, and again it's going to run through all the 500 iterations, and it's hopefully going to obtain a steady result. So we're just going to wait for this to finish. So I'm just going to pause the video till that time. Alright, so looks like the solution is complete. So what I can do is I can just right click on this, and I can set this as the current design point. So now if I go back to project, and what I can do is if I just click on the results again, this time hopefully it should open up design point 2, where the temperature variation should be slightly higher than what we saw before, but all the views, the volume renderings should be preserved. Alright, so let's kind of enable the plane, and what we are going to do is we are just going to hide the volume rendering, and I'm just going to select the plane, and I'm just going to make sure that I color it by the temperature. click apply, and you can see that now the cells are substantially hotter. What you can do is you can play with the range a little bit. You can set up a specified range, so the minimum should be 26 and the maximum should be 30. Let's click on apply. Alright, so now you basically see that this is the new temperature distribution across the cells. Alright, so let me just close this guy, and what I'm going to do is I'm going to run one more design point, which is basically a much more higher value of source, and see how the temperature looks like. And I'm going to add a new value of source, so I'm just going to try 3E5 instead of 3E4, and I'm going to again run 3E5, but this time what I'm going to do is I'm just going to change the inlet velocity to 4 meters per second as well. And we would want to retain all the results, and I'm going to select two cells at the same time using the shift key and right click, and there's an option called update selected design points. So I'm just going to click on this, and okay, so looks like I might be facing a licensing error, so I'm just going to give it a minute to see if it resolves, else I just have to restart it and submit it. In the meantime, I wanted to show you how you can calculate the energy density. So here I'm basically looking at the diameter of each and every cell, right? So you can see that I have one cell where the diameter is 0.01 millimeters. Sorry, this is actually in meters, right? So that's going to be 10 millimeters, and the length of the battery is 50 millimeters or roughly 5 centimeters, and we are saying that there's 2000 joules of energy in that particular cell. Ideally you will have to look at the specifications of a battery to understand what its capacity is, what its energy capacity is, and then what we can basically do is we can calculate the volume, right, of the battery, right? So volume is just pi by 4 d square into h. So I calculate the volume, and what I'm basically saying is I'm saying that this energy is expensed in 3 hours, so the total seconds would be 10,800 seconds. So then what I basically do is I calculate power as energy divided by time, and power density is nothing but power divided by volume. Now ideally you have to multiply this by the number of cells that you have, right? But again, this is just a made up calculation, the numbers are all made up. What I want you to do as part of this project is I want you to measure the dimensions of the batteries using SpaceClaim, and I want you to basically figure out what should be the energy input, what is the right assumption for the time parameter, and then calculate the power density accordingly. So let me just head back to Ansys Workbench, and it looks like the calculation is still in progress. So I'm just going to be pausing the video, and once the results are up, we can take a look at it. Alright, so looks like the solution is up, and you can see that for the same value of each source, when I increased the inlet velocity by 4 meters per second, the temperature did drop by 4 Kelvin, right? Okay, so that's basically how you would simulate a battery thermal management system and then run parametric analysis. So let us assume that the model that we had was a highly accurate computational model of a complex BTMS. Then we can essentially try out different strategies, right? We can basically increase the inlet velocity, and you can actually look at several other quantities such as variance or standard deviation in temperature to understand the non-homogeneity in the temperature, right, in your battery pack. Okay, so that being said, based upon this video, we will be giving you a detailed final project. Take a look at it, and I hope you found this video. All right, thank you guys so much. Bye.